Welcome to the Cosmic Shambles Network. In this series, we're here in Bordeaux in France, and we're here for the 70-second parabolic flight campaign run by the European Space Agency. This particular video is going to be about granular materials, and what that means is all those materials that they're made of lots of little bits, but you can pour out. So imagine sand, salt, sugar, soil, dust, all those kinds of things. Anything you can pour, but is actually a solid, that is a granular material. And actually they're everywhere in our everyday lives. And we know what they do in gravity because all those little bits just fall down. They form piles, sometimes they get jammed, we know what they do. But they are tricky little materials and they're surprisingly unpredictable. And one of the things that's going to be really hard for anyone wanting to go into space, or especially to make stuff in space, is to understand what these little piles of sand or salt or fuel are going to do in different amounts of gravity, because Earth gravity is very unusual in the universe. So we're here to look at the experiments where they're experimenting with simple things like how does a pile of sand behave in zero gravity, and it is well worth finding out. So we're here in a corner of the shed. It's a very nice shed, but it is a bit of a shed here at Novespace. Tell me about the experiment that you're working on here.
Okay, so the experiment is called VidCon, which stands for Vibration-Induced Phenomena in Granular Material. And basically what we have is a chamber where we put particles in, granular matter, in terms of either spheres, that's what we started with, or you can also use anisometric particles like rods that have a certain length and a certain aspect ratio. Yes, and then we are investigating the dynamics when vibrating the system from the sides. So we put some energy into the system and see how it evolves. And independence of what kind of particles we take and what packing fractions we have, how many particles, and also due to the strength of the agitation, we can, for example, observe what we call a gaseous state. So particles are moving around like in a gas you would expect in a normal gas. Or we can go to a more dense system where we have like a big cluster forming in the middle and particles are not moving there, just at the border. So, and we are investigating actually the transition between these two phases.
And where are the places in our solar system, for example? Where might you get plumes, clouds of gas?
Yeah, so for example, in the rings of the Saturn, I think that's basically that you have some dust that is collected in a ring zone. It's not enough material to become a moon, but it is enough to cluster and to make us a thing you can also observe from the Earth actually and see this very beautiful thing.
And I guess later, you know, if we go back to the history of the solar system, there were a lot of very small particles. And
yes,
at some
of course.
Point, they did clump together to become planets.
Yes,
and you need this. You need to understand this sort of process. How do you go from being lots of individual grains of something?
Exactly.
So here we've got an egg timer. It's the epitome of time behaving itself, but that only happens because gravity behaves itself. We're used to these in the kitchen. We're used to what granular materials do. That's what sand does, right? It piles up at the bottom. Perhaps if you add some water, it sticks, you can make a sandcastle. Basically, it piles up. So if we watch the GoPro hit the egg timer here, we can see it flowing through. Hypergravity is about to start. And suddenly it speeds up. So this is where a granular material is behaving like a liquid. But in a second, it's going to enter a bit of an intermediate state. There we go. Zero gravity. Now look at this. This is no good for telling the time. It might be good for telling the time backwards, but it's just swirling around the egg timer. So imagine this was your kitchen cupboard, right? You're not keeping this under control. Imagine this is a factory, or someone has to make medicine to make pills out of. Granular materials, we don't know how they behave. They're really difficult to predict. Back in the hypergravity. But it matters so much because all the things we just take for granted on Earth, if you want to mine in space, if you want to manufacture anything in space, if you want to do 3D printing in space, or if you just want to know that the ingredients in your cupboard are going to stay there, the behaviour of granular materials like this really matters. And that's why it's worth bringing them up here to see what they do in other environments, because they're really difficult to predict. There is no substitute for an experiment. I love this. So I'm gonna draw a diagram, so I like drawing diagrams. You can tell me if I get the diagram wrong. So here, we've got two pistons. So there's one on this side and
Exactly,
one on
yes.
this side like this.
Yes.
And then the thing is that if we had this here on the ground, so there's two pistons like this, and we put some particles in, they would all just sit at the bottom.
Exactly.
So the thing you can do on the plane is that they all sort of space out like
Yes.
this, right?
So we are looking for a homogeneous distribution, which we can achieve due to the zero gravity, and then we start the shaking.
And then the idea is that this is the sort of thing you might find in space, that if there was a collection of dust particles in space.
Exactly. Actually, it has some connections to planetary rings and formation of particles to stars and something like that,
And then, so the pistons sides, they're doing that.
Yes.
And that's because they're like, it's like a pinball machine, they're giving energy.
Exactly. We are continuously putting energy into the system, and then due to the collisions, there will be dissipation,
So this is the interesting thing. So that there's all these interesting bits about this, which is that, because you would think, first of all, the idea of dust in space, it feels, when we look at dust in the house, it just sits there. It doesn't do anything.
That's true,
But when we have dust in space, it is moving, and then things bump into each other.
Exactly, yeah.
But the thing that is interesting, I think, about your experiment, because I think about this like a gas. A physicist thinks of a gas as these perfect hard particles, like snooker balls. That
yes,
bounce
exactly.
off
That's
each
a good
other.
example, just with one more dimension.
So you can imagine this three-dimensional snooker, but the thing that there's a reason you have to keep pumping them, isn't it?
So it is really depending on the amount of particles and the size of the box. So if you cross a critical value of particles, which we call packing fraction, which is the fraction of particles divided by the volume of the cell. If we cross this critical value, then the dissipation in the middle is so big that actually the particles will come to rest and stay there.
So do they stick together, or they just
No. They just dissipate so much energy that the velocity is very low after the collisions.
So it's like, and when you've got really spongy, at the beach sometimes you get really spongy balls, and you throw them, and you throw them, and then they just go. So they lose energy. They don't bounce.
Basically, yes. And but actually, that's exactly the same thing that happens in space also. So you have to go above a critical level in terms of particles, dust, whatever you have. And then, that's another thing, that the gravity starts to set in and keeps them together. But here it's just the dissipation due to the huge number of collisions. And this cluster I'm talking about will always form in the middle of the cell, because the energy input is biggest here, And you always have some particles that can escape from the cluster and bounce back, but then they move this big cluster. You can imagine the mass is much greater than from just one tiny particle, and it loses all the energy. So that's basically what's happening.
So on the flight itself, you've got a little contained box, so you can't touch any of this. It's all sealed away.
Yes, of course. They will never allow us to
let it float out.
Yes.
So inside the pair of pistons right here, there's basically a simulation of a part of the universe, and you can pick your part of the universe in this kind of experiment. So there could be volcanic dust in there could be interplanetary material, all kinds of things hidden inside this experiment, and you can pretend you are almost anywhere in the universe, just inside there. And what are you've got 31 parabolas to play with. Are you changing things in the experiment?
Yes, actually, so it's always 5 parabolas in a row, and afterwards you have a 5 minutes break. And we use all those breaks to inject more particles. So we start with a very small number of particles where we are sure we have a gaseous state. And then at each break we inject some more particles and then repeat the experiments. What we can also do is changing the agitational strengths and in terms of the frequency and the amplitude of the pistons. We can also do some crazy things like an asynchronous shaking, things like that. But this is what we do. So the biggest challenge is adding more particles and then crossing the border and watch what happens.
So you're watching everything on the screen here, and the amazing thing about this is that there's so much detail, such a tiny thing in there, and the only way a human, a scientist, can keep track is through the electronics on the screen. Or you can see little animations as well. And what's happening is that, so you said that at the beginning they behave like a gas, they sort of just bounce off each other, and they might slow down, but they're fundamentally just little particles just bouncing
Exactly,
around.
they don't lose enough energy to stick together. They just it's like pinballs, or the snooker.
But
you
then
said.
at some point they stop, because this is weird. I mean, this is one of those interesting things, I think, because you've already got solid particles, so
Yes.
they should be a solid, but they're behaving like a gas, sort
Yeah,
of.
so that's one crazy thing about granular matter in general. It can behave like a gas, if it's not very dense, but
Yeah.
it can also behave like a solid. Yeah,
And because if you have like a cup of sand, and you pour
exactly,
it out, it behaves like a liquid.
exactly. Or you have these nice sand clocks. Yeah, that's.
And why does that matter? So you talked a bit about, interplanetary matter and dust in between planets and stars.
For example,
why,
yes.
how might this be useful if you're studying that?
Well, the problem about granular matter in general is that there's no real fundamental understanding. So what physicists have been looking for a long time and still are is some general theory for granular material, and this actually is very, very difficult due to what you said, that it can behave like this or like that, independence of how dense the particles are, what kind of particles, what shapes they have. There are so many parameters you have to take into account.
So you could have things that look like jelly babies, or you could have things that look like snooker balls, or you could have things that look like grains of sand,
example,
and they all behave differently, depending on what exactly it is.
Yeah, so we are trying to do our little contribution to a better understanding of this strange but fascinating state of matter. So some people really call it the fourth state of matter, because you cannot really say what is this thing.
And is it just interplanetary stuff, or do you
No.
find uses this in other places?
We are physicists. We are doing really basic research. Yeah, we observe these transitions, and we try to also make some theoretical approach, and then we compare the experiments from the parabolic flight to numerical simulations, for example, and then we are very happy if it matches. And then
And so what sort of particles are you putting in on these flights?
On these flights we are using steel rods with different aspect ratios. So today we were having those kind of particles.
Oh,
So
right.
it is.
They look like the sort of thing that people use to decorate cakes.
Yeah, but you should not eat them.
not
So
eat them,
they are made
steel.
of steel, exactly. Yeah, you have to take into account a lot of things. Yeah, they shouldn't be magnetic because you don't want the influence from the pistons, for example, and they should be heavy enough so that the dissipation works right.
And they can set each other spinning as well. That's the interesting about rods.
Exactly.
Isn't it?
Yeah, it's much easier actually for spheres because they can lose energy due to the collision, but these guys have rotational degrees of freedom as well. Yeah, if you imagine, they will not hit in the center of each other. They're just like this, and then they rotate, and they have rotational and translational energy. It is a very complicated story. So actually, we are putting a lot of brain inside to create a model which we can compare to the sphere model which we have and which really works well. But it seems it's really much more difficult.
When I was growing up, my dad worked in the plastics industry, and there were lots of tiny particles like this for plastics, but they were used in industry, they were used for manufacturing. And the thing that this makes me think of is that if you were, all our manufacturing on Earth assumes you have gravity. It assumes you have gravity that is 9.81 meters per second squared. If you were to take raw material, like a little pellets like this, or plastic pellets, and you took them to the moon, you can't assume your machines are going to work, right?
Of course, that's another thing that has to be taken into account. So basically, that's a good point. So besides all these very fundamental things we are doing, it's also a very important thing if you regard industrial processes. Yeah. So because granular matter is basically everywhere. You have them in the pharmacy, in the beach, everywhere, and they're handled.
Powders, sand, sugar.
Yes, it goes from micrometer
bits.
to meter scale. You can imagine. So granular matter is the coffee you open, or your cereals in the morning. Yeah. So and there are so many strange effects that are not fully understood. That there's a really wide topic. I think we could do this forever.
Well, it'd be nice if you actually got to go to the moon, I guess, one day.
Oh yeah.
Yeah, and actually test some of this out, because it's just so there are so many questions, things we take for granted in the everyday world that just would work differently. You can't assume anything. And so you've done quite a few of these flights now, the parabolic flights. How many have you done?
It's been, I think, the 15th or something like that.
Oh, so you're very familiar with all of
Yeah,
this
and
now.
I've been loving it all the time. So
Yeah.
I remember the first time I flew, I was very afraid what would happen to me.
Yeah.
But then after the first parabola, okay, I'm not getting sick, and it's just a wonderful feeling. I mean, the sad thing is we have really a lot of things to do in the. Yeah, we cannot just.
Can't play.
Yeah, we cannot play.
play.
Sometimes so we have 3 flyers. Sometimes we have like, I don't know, 1 parabola or 2 to get into this free floating zone. But basically, we are very busy, and if something happens, we have to be quick because the distance between the parabolas is just 1 minute.
Yeah. When it is pressure, there's a lot of pressure now, but it's rare. Whereas with you, you've got, you know, like you say, you have a parabola, you've got a problem, you've got 1 minute, go.
Exactly.
Because nothing, you know, the plane is going.
It's a really tough thing, and it goes for 2 hours of really focused work and solving problems, because there will be problems.
Right.
You cannot avoid them. Yeah, you can do 1,000 tests, but the next morning in the plane it will be different.
Isn't experimental science great?
Yes, perfect. That's the point where I admire these theoreticians who just need a pencil and. But
I admire them. I think it's also good for them to see the real world sometimes.
That's true. That's true. We should.
Because you need to check the equations, right? The point is, if you could write down all the equations, you wouldn't need to do this, because you would know.
that's what the theoreticians always say. But I mean, I think we should learn from each other. Yeah, I mean, they have. They make assumptions which might not be the reality, and yeah, with the experiments you can really see how nature behaves. I mean, it's good if you can think of it and make a model, but each model should be tested, experiment, in my opinion. But I'm experimental physicist, so I'm not.
So am I. I'm on your side. And I actually think it isn't science unless you can test it. Like you know, you can't just invent ideas.
Exactly.
And it is a fabulous environment for testing these things.
Yes.
Thank you for watching. Don't forget to like the video on YouTube and to subscribe to Cosmic Shambles to find out all about the many things that we do. There's blogs and podcast videos like this, live events, there's all kinds of stuff going on. And so you should definitely check all of that out. And finally, of course, we owe an enormous amount of gratitude to ESA, to Novespace, and especially to our Patreon supporters for helping us join in with this and helping us share it with you.